Hipparcos was a scientific satellite of the European Space Agency, launched in 1989 and operated until 1993. It was the first space experiment devoted to precision astrometry, the accurate measurement of the positions of celestial objects on the sky. This permitted the accurate determination of proper motions and parallaxes of stars, allowing a determination of the distance and tangential velocity, when combined with radial velocity measurements from spectroscopy. This pinpointed all 6 quantities needed to determine the motion of stars. The resulting Hipparcos catalogue, a high-precision catalogue of more than 118,200 stars, was published in 1997. The lower-precision Tycho catalogue of more than 1 million stars was published at the same time, while the enhanced Tycho II catalogue of 2.5 million stars was published in 2000. Hipparcos' follow-up mission, Sky, was launched in 2013. The word Hipparcos is an acronym for High Precision Parallax Collecting Satellite and also a reference to the ancient Greek astronomer Hipparchus, of Nicaea, who is noted for applications of trigonometry to astronomy and his discovery of the precession of the equinoxes. Background: by the second half of the 20th century, the accurate measurement of star positions from the ground was running into essentially insurmountable barriers to improvements in accuracy, especially for large-angle measurements and systematic terms. Problems were dominated by the effects of the Earth's atmosphere, but were compounded by complex optical terms, thermal and gravitational instrument flexures, and the absence of all-sky visibility. A formal proposal to make these exacting observations from space was first put forward in 1967. Although originally proposed to the French space agency CNES, it was considered too complex and expensive for a single national program. Its acceptance within the European Space Agency scientific program in 1980 was the result of a lengthy process of study and lobbying. The underlying scientific motivation was to determine the physical properties of the stars through the measurement of the distances and space motions, and thus to place theoretical studies of stellar structure and evolution and studies of galactic structure and kinematics on a more secure empirical basis. Observationally, the objective was to provide the positions, parallaxes, and annual proper motions for some 100,000 stars with an unprecedented accuracy of 0.002 arcseconds, a target in practice eventually surpassed by a factor of 2. The name of the space telescope, Hipparcos, was an acronym for High Precision Parallax Collecting Satellite, and it also reflected the name of the ancient Greek astronomer Hipparchus, who is considered the founder of trigonometry and the discoverer of the precession of the equinoxes. Satellite and payload. The spacecraft carried a single, all-reflective, eccentric Schmidt telescope, with an aperture of 29 centimeters. A special beam combining mirror superimposed 2 fields of view, 58 degrees apart, into the common focal plane. This complex mirror consisted of 2 mirrors tilted in opposite directions, each occupying half of the rectangular entrance pupil, and providing an unvignetted field of view of about 1 degree times 1 degree. The telescope used a system of grids at the focal surface, composed of 2,688 alternate opaque and transparent bands, with a period of 1.208 arcsec. Behind this grid system, an image dissector tube with a sensitive field of view of about 38 arcsec diameter converted the modulated light into a sequence of photon counts, from which the phase of the entire pulse train from a star could be derived. The apparent angle between 2 stars in the combined fields of view, modulo the grid period, was obtained from the phase difference of the 2 star pulse trains. Originally targeting the observation of some 100,000 stars, with an astrometric accuracy of about 0.002 arcsec. The final Hipparcos catalogue comprised nearly 120,000 stars with a median accuracy of slightly better than 0.001 arcsec. An additional photomultiplier system viewed a beam splitter in the optical path and was used as a star mapper. Its purpose was to monitor and determine the satellite attitude and, in the process, to gather photometric and astrometric data of all stars down to about 11th magnitude. These measurements were made in two broad bands approximately corresponding to B and V in the UBV photometric system. The positions of these latter stars were to be determined to a precision of 0.03 arcsec, which is a factor of 25 less than the main mission stars, originally targeting the observation of around 400,000 stars. The resulting Tycho catalogue comprised just over 1 million stars, with a subsequent analysis extending this to the Tycho II catalogue of about 2.5 million stars. The attitude of the spacecraft about its center of gravity was controlled to scan the celestial sphere in a regular precessional motion, maintaining a constant inclination between the spin axis and the direction to the Sun. The spacecraft spun around its z-axis at the rate of 11.25 revolutions per day at an angle of 43 degrees to the Sun. The z-axis rotated about the Sun's satellite line at 6.4 revolutions per year. The spacecraft consisted of 2 platforms and 6 vertical panels, all made of aluminum honeycomb. The solar array consisted of 3 deployable sections, generating around 300 W in total. 2 S-band antennas were located on the top and bottom of the spacecraft, providing an omnidirectional downlink data rate of 24 kbit per second. An attitude and orbit control subsystem ensured correct dynamic attitude control and determination during the operational lifetime. Principles. Some key features of the observations were as follows. Through observations from space, the effects of astronomical seeing due to the atmosphere, instrumental gravitational flexure and thermal distortions could be obviated or minimized. All sky visibility permitted a direct linking of the stars observed all over the celestial sphere. The 2 viewing directions of the satellite, separated by a large and suitable angle, resulted in a rigid connection between quasi-instantaneous one-dimensional observations in different parts of the sky. In turn, this led to parallax determinations which are absolute. The continuous ecliptic-based scanning of the satellite resulted in an optimum use of the available observing time, with the resulting catalogue providing reasonably homogeneous sky density and uniform astrometric accuracy over the entire celestial sphere. The various geometrical scan configurations for each star at multiple epochs throughout the 3-year observation program resulted in a dense network of one-dimensional positions from which the barocentric coordinate direction, the parallax, and the object's proper motion could be solved for in what was effectively a global least squares reduction of the totality of observations. The astrometric parameters as well as the standard errors and correlation coefficients were derived in the process. Since the number of independent geometrical observations per object was large compared with the number of unknowns for the standard model, astrometric solutions not complying with this simple 5-parameter model could be expanded to take into account the effects of double or multiple stars, or nonlinear photocentric motions ascribed to unresolved astrometric binaries. A somewhat larger number of actual observations per object, of order 110, provided accurate and homogeneous photometric information for each star, from which mean magnitudes, variability amplitudes, and in many cases period and variability type classification could be undertaken. Development, launch and operations. The Hipparcos satellite was financed and managed under the overall authority of the European Space Agency. The main industrial contractors were Matra Marconi Space and Alenia Spazio. Other hardware components were supplied as follows: the beam-combining mirror from REOSC at St. Pierre du Perret, the spherical, folding and relay mirrors from Carl Zeiss in Oberkochen, the external straylight baffles from CASA in Madrid, the modulating grid from CSEM in Neuchâtel, the mechanism control system and the thermal control electronics from Dornier Satellite Systems in Friedrichshafen, optical filters, the experiment structures and the attitude and orbit control system from Matra Marconi Space in Velocity, instrument switching mechanisms from Alicon Contraves in Zurich, the image dissector tube and photomultiply detectors assembled by the Dutch Space Research Organization, SRON in the Netherlands, the refocusing assembly mechanism designed by TNOTPD in Delft, the electrical power subsystem from British Aerospace in Bristol, the structure and reaction control system from Daimler-Benz Aerospace in Bremen, the solar arrays and thermal control system from Fokker Space System in Leiden, the data handling and telecommunications system from Saab Ericsson Space in Gothenburg, and the apogee boost motor from September, in France. Groups from the Institut d'Astrophysique in Liège and the Laboratoire d'Astronomie Spatiale in Marseille contributed optical performance, calibration and alignment test procedures. Captech in Dublin and Logica in London contributed to the onboard software and calibration. The Hipparcos satellite was launched on an Ariane 4 launch vehicle, Flight V33, from Kourou, French Guiana, on 8 August 1989. Launched into a geostationary transfer orbit, the Mach 2 apogee boost motor failed to fire, and the intended geostationary orbit was never achieved. However, with the addition of further ground stations, in addition to the primary ground station at Odenwald in Germany, the satellite was successfully operated in its geostationary transfer orbit for almost 3.5 years. All of the original mission goals were eventually exceeded. The satellite was operated by the ESA Operations Control Center at ESOC, Darmstadt, including an estimate for the scientific activities related to the satellite observations and data processing. Hipparcos mission cost about €600 million, and its execution involved some 200 European scientists and more than 2,000 individuals in European industry. Hipparcos Input Catalogue. The satellite observations relied on a predefined list of target stars. Stars were observed as the satellite rotated, by a sensitive region of the image dissector tube detector. This predefined star list formed the Hipparcos Input Catalogue. Each star in the final Hipparcos Catalogue was contained in the Input Catalogue. The Input Catalogue was compiled by the Inca Consortium over the period 1982 to 89, finalized pre-launch, and published both digitally and in printed form. Although fully superseded by the satellite results, it nevertheless includes supplemental information on multiple system components as well as compilations of radial velocities and spectral types, which, not observed by the satellite, were not included in the published Hipparcos catalogue. Constraints on total observing time, and on the uniformity of stars across the celestial sphere for satellite operations and data analysis, led to an input catalogue of some 118,000 stars. It merged two components. First, a survey of around 58,000 objects as complete as possible to the following limiting magnitudes: V and LT 7.9 plus 1.1 sin B for spectral types earlier than G5, and V and LT 7.3 plus 1.1 sin B for spectral types later than G5. Stars constituting this survey are flagged in the Hipparcos catalogue. The second component comprised additional stars selected according to the scientific interest, with none fainter than about magnitude V equals 13 mag. These were selected from around 200 scientific proposals submitted on the basis of an invitation for proposals issued by ESA in 1982, and prioritized by the Scientific Proposal Selection Committee in consultation with the Input Catalogue Consortium. This selection had to balance a priori scientific interest and the observing program's limiting magnitude, total observing time, and sky uniformity constraints. Data reductions. For the main mission results, the data analysis was carried out by two independent scientific teams, NDAC and FAST, together comprising some 100 astronomers and scientists, mostly from European institutes. The analyses, proceeding from nearly 1,000 GBIT of satellite data, required over 3.5 years, incorporated a comprehensive system of cross-checking and validation, and is described in detail in the published catalogue. A detailed optical calibration model was included to map the transformation from sky to instrumental coordinates. Its adequacy could be verified by the detailed measurement residuals. The Earth's orbit and the satellite's orbit with respect to the Earth were essential for describing the location of the observer at each epoch of observation, and were supplied by an appropriate Earth ephemeris combined with accurate satellite ranging. Corrections due to special relativity made use of the corresponding satellite velocity. Modifications due to general relativistic light bending were significant and corrected for deterministically assuming gamma equals 1 in the ppn formalism. Residuals were examined to establish limits on any deviations from this general relativistic value, and no significant discrepancies were found. The Hipparcos reference frame. The satellite observations essentially yielded highly accurate relative positions of stars with respect to each other throughout the measurement period. In the absence of direct observations of extragalactic sources, the resulting rigid reference frame was transformed to an inertial frame of reference linked to extragalactic sources. This allows surveys at different wavelengths to be directly correlated with the Hipparcos stars, and ensures that the catalogue proper motions are, as far as possible, kinematically non-rotating. The determination of the relevant three solid body rotation angles and the three time-dependent rotation rates was conducted and completed in advance of the catalogue publication. This resulted in an accurate but indirect link to an inertial extragalactic reference frame. A variety of methods to establish this reference frame link before catalogue publication were included in appropriately weighted interferometric observations of radio stars by VLBI networks, Merlin and VLA observations of quasars relative to Hipparcos stars using CCDs, photographic plates, and the Hubble Space Telescope photographic programs to determine stellar proper motions with respect to extragalactic objects, and comparison of Earth rotation parameters obtained by VLBI and by ground-based optical observations of Hipparcos stars. Although very different in terms of instruments, observational methods and objects involved, the various techniques generally agreed to within 10 millisec in the orientation and 1 millisec per year in the rotation of the system. From appropriate weighting, The coordinate axes defined by the published catalogue are believed to be aligned with the extragalactic radio frame to within plus or minus 0.6 millisec at the epoch J1991.25, and non-rotating with respect to distant extragalactic objects to within plus or minus 0.25 millisec year. The Hipparcos and Tycho catalogues were then constructed such that the Hipparcos reference frame coincides to within observational uncertainties with the International Celestial Reference System, and representing the best estimates at the time of the catalogue completion. The resulting Hipparcos reference frame is thus the materialization of the ICRS in the optical. It extends and improves the J2000 system, retaining approximately the global orientation of that system but without its regional errors, double and multiple stars. Whilst of enormous astronomical importance, double stars and multiple stars provided considerable complications to the observations and to the data analysis. The data processing classified the astrometric solutions as follows: single star solutions, 100,038 entries, of which 6,763 were flagged as suspected double component solutions, 13,211 entries, comprising 24,588 components in 12,195 solutions. Acceleration solutions, 2,622 solutions. Orbital solutions, 235 entries. Variability-induced movers, 288 entries. Stochastic solutions, 1,561 entries. No valid astrometric solution, 263 entries. If a binary star has a long orbital period such that nonlinear motions of the photocenter were insignificant over the short measurement duration, the binary nature of the star would pass unrecognized by Hipparcos, but could show as a Hipparcos proper motion discrepant compared to those established from long temporal baseline proper motion programs on ground. Higher-order photocentric motions could be represented by a 7-parameter or even 9-parameter model fit, and typically such models could be enhanced in complexity until suitable fits were obtained. A complete orbit requiring 7 elements was determined for 45 systems. Orbital periods close to 1 year can become degenerate with the parallax, resulting in unreliable solutions for both. Higher-order systems provided further challenges to the data processing. Photometric observations. The highest accuracy photometric data were provided as a byproduct of the main mission astrometric observations. They were made in a broadband visible light passband, specific to Hipparcos, and designated HP. The median photometric precision for HP and LT 9 mag was 0.0015 mag, with typically 110 distinct observations per star throughout the 3.5-YAR observation period. As part of the data reductions and catalog production, new variables were identified and designated with appropriate variable star identifiers. Variable stars were classified as periodic or unsolved variables. The former were published with estimates of the period, variability amplitude, and variability type. In total, some 11,597 variable objects were detected, of which 8,237 were newly classified as variable. There are, for example, 273 Cepheid variables, 186 RLYR variables, 108 Delta Scuti variables, and 917 eclipsing binary stars. stars. The star mapper observations, constituting the Tycho catalogue, provided two colors, roughly B and V, in the Johnson-UBV photometric system, important for spectral classification and effective temperature determination. Radial velocities. Classical astrometry concerns only motions in the plane of the sky and ignores the star's radial velocity, i.e., its space motion along the line of sight. Whilst critical for an understanding of stellar kinematics, and hence population dynamics, its effect is generally imperceptible to astrometric measurements, and therefore it is generally ignored in large-scale astrometric surveys. In practice, it can be measured as a Doppler shift of the spectral lines. More strictly, however, the radial velocity does enter a rigorous astrometric formulation. Specifically, a space velocity along the line of sight means that the transformation from tangential linear velocity to proper motion is a function of time. The resulting effect of secular or perspective acceleration is the interpretation of a transverse acceleration actually arising from a purely linear space velocity with a significant radial component, with the positional effect proportional to the product of the parallax, the proper motion, and the radial velocity. At the accuracy levels of Hipparcos, it is of importance only for the nearest stars with the largest radial velocities and proper motions, but was accounted for in the 21 cases for which the accumulated positional effect over 2 years exceeds 0.1 millisecond. Radial velocities for Hipparcos Catalogues stars, to the extent that they are presently known from independent ground-based surveys, can be found from the astronomical database of the Centre de Données Astronomiques de Strasbourg. The absence of reliable distances for the majority of stars means that the angular measurements made astrometrically in the plane of the sky cannot generally be converted into true space velocities in the plane of the sky. For this reason, astrometry characterizes the transverse motions of stars in angular measure rather than in kilometer per second or equivalent. Similarly, the typical absence of reliable radial velocities means that the transverse space motion is, in any case, only a component of the complete three-dimensional space velocity. Published catalogues. The final Hipparcos catalogue was the result of the critical comparison and merging of the two analyses, and contains 118,218 entries, corresponding to an average of some 3 stars per square degree over the entire sky. Median precision of the 5 astrometric parameters exceeded the original mission goals, and are between 0.6 to 1.0 mass. Some 20,000 distances were determined to better than 10% and 50,000 to better than 20%. The inferred ratio of external to standard errors is approximately equals 1.0 to 1.2, and estimated systematic errors are below 0.1 mass. The number of solved to suspected double or multiple stars is 23,882. Photometric observations yielded multi-epoch photometry with a mean number of 110 observations per star, and a median photometric precision of 0.0015 mag, with 11,597 entries were identified as variable or possibly variable. For the star mapper results, the data analysis was carried out by the Tycho Data Analysis Consortium. The Tycho catalogue comprises more than 1 million stars with 20 to 30 millisecond astrometry and 2-color photometry. The final Hipparcos and Tycho catalogues were completed in August 1996. The catalogues were published by ESA on behalf of the scientific teams in June 1997. A more extensive analysis of the star mapper data extracted additional faint stars from the data stream, combined with old photographic plate observations made several decades earlier as part of the astrographic catalog program. The Tycho II catalog of more than 2.5 million stars was published in 2000. The Hipparcos and Tycho I catalogues were used to create the Millennium Star Atlas, an all-sky atlas of 1 million stars to visual magnitude 11. Some 10,000 non-stellar objects are also included to complement the catalog data. Between 1997 and 2007, investigations into subtle effects in the satellite attitude and instrument calibration continued. A number of effects in the data that had not been fully accounted for were studied, such as scan phase discontinuities and micrometeoroid-induced attitude jumps. A re-reduction of the associated steps of the analysis was eventually undertaken. This has led to improved astrometric accuracies for stars brighter than HP equals 9.0 mag, reaching a factor of about 3 for the brightest stars, while also underlining the conclusion that the Hipparcos catalog as originally published is generally reliable within the quoted accuracies. All catalog data are available online from the Centre de Données Astronomiques de Strasbourg.